Hi, I'm Roswell,
I'm Jesus.
and this is the LT32 processor. It's just the initial of our last name with a 32-bit space processor. So to start, we're going to be doing a brief overview of the instruction set architecture. Then we're going to go over how it was implemented in hardware. Then we're going to go over the input-output system, and then we'll be finishing up with the stack-based interrupts. So first, here's the instruction set architecture. First thing to talk about is the memory structure. It's hardware architecture, which means the data and instruction memory are separate and served separately by the CPU. And it also has up to byte resolution addressability. And it's also in big endian format, which means the most significant bits are stored first. And so to talk about some important registers, first one would be the flags register, which carries the interrupt enable, carry, overflow, negative, and zero flags. And then we have 32 general purpose registers. Some important ones are 0, which are hard-coded to obey all zeros, the stack pointer, which will point to the top of the stack, and the return address, which will be used for jump and link. So there are two main data types. They're both 32-bit. One is signed and one is unsigned. For the signed, the MSB determines the sign. So it has up to it can reach from -2 million to 2 million. So an example would be if it's FFFF000A, we hit -65,000. And if it's unsigned, we can double the potential range in the positive side. And so that same hex value would become 4 million instead. There are three main addressing modes. First one being immediate, and that's where it can be a 16 or 26-bit mode where the operand is part of the instruction, and the register is where the source and destination operand values are specified in a register. Then the next one would be register indirect, where the effective address is in memory pointed by a register plus the offset, rather than in the instruction itself. So here's the three formats for the instruction types, R, I, and J. So for R, we have the 6-bit opcode, followed by two sources and a destination, followed by the optional shift amount to be used in the barrel shifter, and the function code. Then we have the I type, which also has a 6-bit opcode, two sources, and 16-bit immediate value. Then we have the J type, which has the opcode as well, and the 26-bit immediate, which is concatenated with the upper 4 bits of the program counter and 2 zeros at the end. So here are the three, all the instructions supported, organized alphabetically by category.
So now I'm going to be going over the hardware implementation. So this is a top-level overview of our CPU. We have our CPU module, our memory, and then our I/O, which also contains memory. And these are all interconnected using control signals, addresses to address the data memory and the I/O memory, as well as data in order to read and write from data memory and I/O memory. So this is an overview of our CPU module. We have our data path, an instruction unit, and a control unit. Our control unit is a finite state machine that sends out control signals to our integer data path as well as our instruction unit. Our instruction unit and data path are connected, but the only thing that goes between them are data buses. There are no control signals that go from one to the other. So this is our integer data path. We have our register file that contains our 32-bit general purpose registers. Then we have two intermediary registers, RS and RT, that hold data from the register file or other sources. Then we have our ALU, which outputs our status flags, our carry, overflow, negative, and zero. Our ALU has two separate 32-bit outputs that are output to more intermediary registers. There's our DIN register, which holds data out from either data memory or I/O memory. We have our ALU out, which stores the result of our ALU operation. And then we have low and high registers for division and multiplication. And then all of these are multiplexed in another mux that feeds to our ALU out, which is a data bus. So this is the inside of our ALU. We have four separate combinational modules. First is going to be our MIPS32 module. This does all of our arithmetic and logical operations. We have a division module and a multiplication module. And then we have a shift module that we added. This takes in an input from T and a variable shift amount specified by this field for our R-type instructions. And it variably shifts the T input anywhere from 0 to 31 times, depending on what shift amount is, the value of shift amount. And then all of these outputs are multiplexed as well as the flags that they produce for our output of our ALU.
Is there any reason why there's two Y highs on your barrel shifter? Is that just a typo?
Oh, that's just a typo.
Okay.
This is the inside of our instruction unit. We have our program counter. This is used as a pointer to memory in our instruction memory, where all of our instructions are stored. That gets fed into our instruction register, which holds the contents of our instruction memory, the output of our instruction memory, sorry. The lower 16 bits of this is concatenated using a sign extension module, and what this does is it allows us to use the 16-bit immediate values for our I-type instructions.
So now we're going to be talking about the control states for each major type of instruction. First one being the R type. So first we have fetch. That's going to be in parallel or the same as all the other instructions. Then we have decode. If the opcode is 0, we'll know that it's an R type, and then we'll load the RS and the RT with their corresponding instructions. Then we'll move on to the actual ALU operation itself, determined by the function code. From there, we then go back to write back ALU, and that's going to state that the destination is determined by the RD register, and then we go back to fetch again. So the next one will be the I-type, and that's where the fetch will also be the same. Now, this time, decode will, when the opcode is not 0, we'll know to load the RS and the immediate field values. And then next we'll go to the I-type, and that's where the ALU will operate itself, and it'll store it to ALU out. And then in write back immediate, we'll know to get contents of the ALU out and store it to the RT destination. And then we go back to fetch. So the next one would be the branch, and so fetch will also be the same, but in this time decode will tell us which kind of branch to perform. Then we'll perform the effective address calculation with the ALU, and it'll modify those flags. From there, we then check those flags, and then we branch if we wanted to branch, or we do not branch if we do not want to branch, and we proceed to the next stage. So the next one will be the J type. So same thing again, fetch will be the same, decode will determine whether to jump or to perform a jumping link. Then the third state will be to perform the actual jump by loading the program counter with the 26-bit immediate with the upper 4 bits of program counter concatenated with 2 bits of the 2 0 bits at the end. And we go back to fetch. So now we're going to be addressing the input and output. So here's our block diagram. It's addressable with 1K by 32, so it's word addressable. And so it has familiar inputs such as read, write, chip select, and address, and along with DN. And here we also have a method to generate an interrupt. So when interrupts, so it'll generate a request whenever, or it'll push out it'll push out a receive after it has an acknowledge. So here's input from memory. The main thing to know about input is that it's basically just like a load word, but when you're interfacing with memory. So here are the 3 main states. We're saying that the ALU out will get an effective address calculation of the RS plus the sign extended immediate. Then we'll then load that ALU out into DN, and DN will have the memory, the IO memory pointed by that ALU out. And we go back to pushing it back into the RT register from the contents of the DN. So next we have output, and that's going to be essentially like store word, but interfacing with memory instead. So there are 2 main ones. So just like before, we're going to perform an effective address calculation with adding the RS and the sign extended 16-bit value. And we'll also be loading RT with the contents of the RT from the instruction. And then from there, we're going to load the IO pointed by that effective address calculation with the contents of RT. So here is our validation for the input or output. And here we can see in the orange box that that output will perform the right calculations. In order to perform this, we have to have additional hardware. And so we're going to multiplex the D input with IO read. And if IO read is asserted, we'll take the output of the input-output system. And if it isn't, we'll just take it like normal from the data memory out.
So now we'll be talking about how we implemented stack-based interrupts in our architecture. So just a brief overview on how we have interrupts in our system. We have an interrupt request signal which comes from an external source. Whenever our CPU receives that interrupt request, the very first thing it does is it checks to see if our interrupt enable flag is set to 1. If it's not, it will completely ignore the request. If it is, it will pre-decrement our stack pointer and save first our program counter and then our current state of our flags. Afterwards, it'll load our program counter with whatever is in data memory pointed at by our interrupt vector, which for our design happens to be 0x3fc. After it finishes all of its interrupt states, it will set our interrupt acknowledge signal high, letting our external device know that we are in the middle of the interrupt service routine. So a few hardware additions that we had to do in order to implement our stack-based interrupts. The very first thing we had to do is we had to add this multiplexer to our S address of our register file. And this selects between the S address input, which comes from the instruction register, as well as a hard-coded 0x1D. Now this 1D allows us to directly address our stack pointer as an output, regardless of whatever our S address is from our instruction register. Next, we had to also multiplex our RS register. We extended our T-select control signal to be 3 bits. So whenever the most significant bit is set to 1, we input whatever is being output of, whatever the ALU output has. And that allows us to feed the results of the ALU back into RS in order for us to save a state, which I'll explain briefly. Additionally, we also had to extend our T-select mux into our RT register in order to choose between our program counter in as well as our flags from our control unit. Now this is sign extended in our control unit to be 32 bits, so we concatenate 27 bits of 0 with our flags in order to have a 32-bit value. So these are our interrupt states. The very first thing that we do is that we get the stack pointer of our value when we're starting our interrupt states, and then we decrement it by 4 since it is a pre-decrement. Next, we put, in the same state, we put our program counter into RT. RT is used as the data out of our data path in order to be input into memory. So this is where we set up to save our program counter in our memory. Now we use the stack pointer -4 as a pointer in data memory, and we save our program counter in data memory at that location. Then we at the same state, we load RS with that result. We do not write to the register file. This saves us an extra state of having to write to the register file and then read from it.
Right.
Next, we subtract that stack pointer value again. And now we prepare our flags to be put in our memory. And again, it's already concatenated. Now we use the stack pointer -8 as a pointer in memory, and we save our flags. And we also have to save our new stack pointer value in our register file, as to not lose our place in the stack. Additionally, since we have a hard-coded interrupt service routine vector, we save that in our ALU out register, which is the output of our ALU. And then we use that as a pointer to pull in data from memory into our DIN register. Finally, we load our program counter with whatever is in DIN pointed at by our interrupt service routine vector, and then we also set our interrupt acknowledge signal high to let our external device know that we're in the middle of our interrupt.
Excellent.
So when we return from interrupt, we do the same thing in reverse. So we're using a post increment for this. So first we get our stack pointer, and then we just pass our stack pointer value through. We do not increase it. And we use that as a pointer in memory to get whatever is in memory at that location. Now we know that since we saved our flags second, the first thing that's going to pop off of our stack is going to be our flags. So we save that in our data in register. And then we load, we basically just feed the output of our ALU back into RS. Again, we don't put it in the register file to save the state. Now that we know that our flags are in DIN, we put whatever's in DIN in our flags. We just chop off the 27 bits of 0 and then load the 5 bits into our flags into our control unit. And then we increment our stack pointer by 4 to go to the next location in memory in our stack. So now we use that as a pointer, and we put whatever's on the stack, which we know at this point is our program counter, into our DIN register. And then we feed that stack pointer value back into RS. We need to increment it one more time in order to get to the original location in order to get the original value of our stack pointer. So in this state, we increment it by 4, again, to get that original value. And then we load our program counter with whatever's in DIN, because we know that since we saved our program counter first, it's going to be the second thing that we pop off the stack. Finally, we have to save our new stack pointer value, which is the stack pointer +8, into our register file. So this is the output of our 14th memory module for the submission of our project. We modified it slightly to output the contents of our data memory, and the original value of our stack pointer is 3FC, as shown here. When we decrement it by 4, which is the first thing we did in our interrupt request, or interrupt service routine, sorry, you can see that our program counter is saved here.
Right.
Now, since we don't actually delete what's on the stack, we just change the value of our stack pointer, it's saved even after the execution of the instructions in our 14th memory files. Additionally, above that is our flags. Now, not all of the flags are set to 1 or a 0. Some are set to X because we don't care when we do certain operations. So you can see that that's stored here. And then here's just another location of memory where we didn't actually modify it because we didn't write to memory at that location. So finally, we have an asynchronous reset, which is just an external input into our CPU. What it does is it basically forces our control unit to go to a reset state. Now, in this reset state, we reset the value of our program counter to 0. Additionally, we set the value of our stack pointer to 3FC. That's just a hard-coded value that we set it at. And then we reset all of our flags down to 0. So if the interrupted enable flag was set high, it's now set low, and we have to set it again. So for future enhancements, we didn't finish doing an enhancement that we wanted to, so we decided not to include it in our presentation. But we were working on a floating point data path, which had a separate, it was an entirely separate module that had its own register file and ALU. But in the future, we do plan on finishing single and double precision floating point instructions.
What was the hang-up with that?
Just ran out of time.
Just ran out of time with the floating point. Any other questions? Okay, thank you very much.